This is now the second part of chapter 3, and we will work on properties of alkanes, some physical properties of alkanes, and then also look at conformations, the stereochemistry of alkanes. So alkanes are called as paraffins, which means little affinity or low affinity compounds, because they have less affinity to react with other substances, and they are mostly inert in nature. Okay? The carbon's valency is fulfilled in all the alkanes, therefore they have no tendency to react most of the time. They do, however, react with oxygen and halogens, and a few reactions we can look here. For example, this reaction shows methane completely reacting with oxygen to form carbon dioxide and water, and this will be a combustion reaction, and a large amount of heat is released with this reaction. Okay? Then the reaction with the chlorine, this is with halogens, and so this example here shows with chlorine. So when an alkane is irradiated with light, okay, in presence of light, this reaction happens, where H nu here stands for light, okay, LiGT, okay, all right. So here it is H nu, where it is H is the Planck's constant and nu is the Greek letter nu for frequency. And depending on the time allowed and the relative amounts of the two reactants, we can get a subsequential reaction of the alkane, where every time you see a hydrogen atom is replaced with a chlorine atom. Okay, so actually this is kind of a chain reaction that once it starts, you get a mixture of all these products. You will get chloromethane or dichloromethane. This is chloroform and carbon tetrachloride. Okay, so we get a mixture. It's not a very useful reaction. However, still this is a very common reaction for alkanes, that when they react in presence of halogens, subsequently one hydrogen is replaced with the halogen. Regarding some other physical properties, alkanes show increase in their melting point and boiling points as the size increases. Okay, so for example, you can see with this graph here that as the number of carbon atoms increases, the melting point and boiling point will increase. And this is the reason is because of the London dispersion force, that as we increase the number of carbon atoms, there is a higher degree of London dispersion force, which causes the boiling points and melting points to increase. However, if we look at branching, okay, another effect that is seen in the alkane's physical property is that as the branching increases, it lowers the alkane's melting point. Okay, so for example, here we have a straight chain alkane, and here we have a branched chain alkane. You can see that the branched chain alkane has a lower boiling point than the straight chain alkane. Right? So the reason is that as the branching increases, they are more and more spherical than straight chains, or they have lesser surface area, and therefore they have smaller London dispersion force. Okay, so if you look something like this, this is an example of butane, and if you compare it with its branched isomer, you can see that you have a more spherical shape here, right? So less surface area. This is less surface area, as a result of which there are lesser London dispersion forces, and that causes the boiling point to decrease. Okay. So this is an example which is asking that which compound will have a tendency to have a higher boiling point. First question is between octane and nonane. Octane is an 8 carbon atom alkane, nonane is a 9 carbon atom alkane. So as we said earlier, that the larger the number of carbon atoms, more is the boiling point. Therefore, nonane will have a higher boiling point. Okay. In this next one, we have octane, which is like 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so we are solving question B now. And then we have 2,2,3,3 tetramethyl butane. Okay, so that it is, you are comparing it with 2,2,3,3 tetramethyl butane. Okay, now if you look at these, both are isomers. They have the same molecular formula, but one is a straight chain and the other is a branch chain. So we just learned that the straight chain alkane will have a higher boiling point. So octane will have a higher boiling point and the branched alkane will have a lower boiling point. All right, and so that's about a couple of chemical properties and some physical properties of alkanes. The next topic is talking about conformations of alkanes. Now, so far, we have only looked at molecules in a two-dimensional way. But now we are looking at a three-dimensional structure of molecules. And here is where we introduce the stereochemistry aspect of stereochemistry. And conformation, we talk about conformation when different arrangement of atoms due to free bond rotation. Okay, so that is what is called as conformations. So carbon-carbon single bonds, they can freely rotate along the sigma bond axis, and the different arrangements that are obtained, these are called as conformations. Okay, and conformers can be isolated. They cannot be isolated because they rapidly rotate. So if you have a conformation of ethane, and then the other conformation of ethane is eclipsed. So we have a staggered and an eclipsed conformation that is interchangeable, but you cannot isolate either one of them because it happens very, very fast. The free bond rotation giving rise to these arrangements is happens very rapidly. Now, this is an important branch of chemistry called as conformational analysis, and it is important for us to know how a drug molecule can interact with its target by adopting the most stable conformation. So this part of chemistry, which is called as conformational analysis of organic compounds, is very, very important in drug design. So we will start the study with simple molecules like ethane. Okay, I'm just going to skip this slide and move on to the next one. Okay, so the main things that we need to learn regarding conformations is you should be able to draw what is called as Newman projections, where we view the carbon-carbon atom bond directly end on, and it represents two carbon atoms by a circle. I'll show it to you in a minute. So you need to know how to draw Newman projections. You also should know the meaning of gauche, anti, eclipsed, and staggered conformations, and then also be able to estimate the relative energies of different conformations of alkanes, because some conformers are more stable than the others. So you should be able to give an idea of why one conformer would be more stable than the other. And also, if you're given the values of the interaction between different groups, then you should be able to calculate the relative energies of different conformations of the alkanes. So the two main types of conformations for ethane are called as staggered and eclipsed. In staggered, the most stable, which is the most stable conformer, all the 6 carbon-hydrogen bonds are as far away as possible. Okay, and in eclipsed, the least stable, all 6 hydrogen bonds are as close as possible to each other. Okay, so here are the two structures where so here is the two different structures where you can see that the first one is the eclipsed one, then comes the staggered, then eclipsed and staggered, and so on. So this is arising due to free rotation around the carbon-carbon single bond of ethane along these are represented by as a graph where we are plotting the energy versus the dihedral angle. Okay, so as we do a 60-degree rotation every time, the conformer changes from an eclipsed to a staggered, then from a staggered to an eclipsed, and so on. Okay, so if you learn to draw one more time. Okay. The way we would draw the conformers of ethane are, again, this is your molecule of ethane, where you have the 3 hydrogen atoms, and then you have another 3 hydrogen atoms in the front carbon atom, right? So we want to put a color to this. Let's put a green color to the front carbon atom and a red color to the back carbon atom. The way we would represent the ethane conformer is the front carbon atom is represented by a dark circle, and then you draw out the 3 hydrogen atoms that are attached to it. Okay. And then the back carbon atom is drawn as an empty circle, and then the hydrogens are attached to the edge of the back circle. Okay, so these are the hydrogens that are on the back one, and then the front one hydrogens are these ones, the one which I have represented in green color. Okay, so this one, if you see, the hydrogen atoms are as far apart from each other. This is what is called as the staggered, okay, staggered conformer, and when I rotate it through a 60-degree along the dihedral angle is this hydrogen, carbon, hydrogen, okay, so that's the dihedral angle. You can get the eclipsed, the other conformer, where again you can keep the front carbon atom intact. Okay? Front carbon atom we don't rotate, so think like a wheel, and you are rotating it either to the clockwise or anti-clockwise. So say I am rotating the back carbon atom, which is my circular wheel, to the clockwise direction. Okay, so this way. So then what happens is I get the next conformer where this hydrogen moves behind this hydrogen, right, the green one. The pink hydrogen again goes behind, and then the other hydrogen also again goes behind. So this conformer is what is called as the eclipsed. So if you see, the eclipsed conformer is more in energy because here the hydrogen atoms are closer to each other. Okay, so there is about 4 kilojoules of energy when they are interacting with each other, and that strain, we call this as a torsional strain. So that's the in an eclipse conformer, there is torsional strain between the hydrogen atoms, and it is caused by the interaction of the carbon-hydrogen bonding orbitals on the carbon's anti-bonding orbitals. Okay? Major factor is an interaction between the CH bonding orbitals on one carbon with the anti-bonding orbitals on the adjacent carbon, and this makes the staggered conformer more stable because now the hydrogen atoms are not as closely interacting as in the eclipsed conformer. And the difference in energy from the staggered to the eclipsed is about 12 kilojoules per mole. So the staggered is more stable from the eclipsed by about 12 kilojoules. Okay, and that is what we are seeing in this energy diagram. We see that this is the eclipse, we at a higher energy position, then we come to staggered, it comes to a lower energy, then again it goes to a eclipse, energy increases, comes to a staggered, the energy decreases, and so on. Okay, and you can see that the difference in energy between the eclipse and the staggered is 12 kilojoules per mole, and the reason is the interaction of 2 hydrogen atoms. Torsional strain is about 4. Okay, so when these 2 interact, it's 4 kilojoules. These 2 interact, it is another 4 kilojoules. per mole, okay, and then these two interact, it is another 4 kilojoules per mole. So 3 times 4 is 12. So that's how you come up with this value of 12 kilojoules per mole, where the staggered is more stable than the eclipsed. And you can extrapolate these to other molecules. As the number of carbon atom increases, you can see different variations in this conformational analysis. But for propane, it's pretty much similar. Let's try out for propane. Okay, we can again use a slide here to understand it. Okay, so for propane, we can first draw out the normal line structure for propane. It's 3 carbon atom. If you recall, propane is C3H8. So the structure is like this. Three carbon atom. Now each of these carbon atoms have hydrogens, right? So we have 1, 2, and 3. Then we have 2 hydrogen atoms here, and then we have 3 here, correct? So the way we portray the conformations of this propane is by saying that, okay, you keep your eye for looking through any 2 of the carbon atoms. Okay, so if you label them as C1, C2, and C3, say this is my C1, it's my C2 and C3, and if you are looking through here, if your eye is here and you're looking through here, so this becomes my front carbon atom, this green one, and then this one becomes my back carbon atom. So once you identify the front and the back carbon atom, you can look at what are the groups that are attached to these carbon atoms. Okay, so we will draw the front one first. So here is my front. Remember, we said that the front carbon atom is represented as a dark circle. So we go ahead and add the 3 hydrogen atoms that are attached to it. So 1 hydrogen, the 2nd hydrogen, and the 3rd. Okay, the back carbon atom is represented as an empty circle. So this is how we represented the back carbon atom. Now, what are the groups that are attached to it? 2 hydrogens and then a CH3, right? So this is a CH3. So we don't have to separate them out, just take this whole thing as a CH3 group and 2 hydrogens, right? And again, the way we can start by eclipsed or staggered. I'm doing a staggered first. So the 2 hydrogens, so these 2 hydrogens. And then this one, actually, I'm going to erase it and write it as CH3 for simplicity purposes. Okay, so this is my CH3. So I have a 2 hydrogens and a CH3 group. So that's how I represent my propane. So front carbon atom, back carbon atom, and the other CH3 that is attached to it. This would be the most stable one because every hydrogen atom and the CH3 groups are as far apart as possible. So this one would be the staggered conformation of propane. Now if I do a 60-degree rotation along the dihedral angle, what do I get? An eclipse conformer, where my front carbon atom is again represented by a dark circle. We have the 3 hydrogen atoms attached to it. So it's always good to keep one of the carbons intact and just rotate the other one. So I like to keep the front carbon atom intact in this way and just rotate the back carbon atom. Okay, so and also make sure that you rotate it in one direction so that you are know which are the conformations that it is giving rise to. So I'm rotating it in the clockwise direction. So the pink hydrogen atom goes behind this green one. Then the CH3 will go behind this hydrogen atom, right? And then we have the other hydrogen behind this. So this, if you look at this, now we have closer interaction between the different atoms. So this will be my eclipsed conformer. Eclipsed conformer, which is my less stable conformer. And the reason here is again the same as we said before, that the torsional strain that arises between the hydrogen atoms and the methyl group and the hydrogen atom here. So will it be again 12 kilojoules like in ethane? It will not, because now in ethane you had the three sets of interaction of hydrogen atoms, right? But in this case, you have these two hydrogen atom interacts and it pertains to 4.0 kilojoules per mole. These two hydrogens interact, and that again is 4.0 kilojoules per mole. But here now you have a torsional strain due to interaction between a CH3 and a H group. Now CH3 is a larger group, so the interaction will be slightly higher, and the torsion strain would be slightly higher, and this is about 6 kilojoules per mole. Okay, so if you add them up, it comes up to be 14 kilojoules per mole. Okay, so in case of propane, the here is propane. You can see 6 kilojoules per mole because of interaction between the hydrogen and the CH3, and the other two hydrogens are 4 kilojoules per mole. So if I were to draw the energy diagram for propane, it would be very similar to that of ethane. It would be very similar to that of ethane, except that the difference in energy, plot potential energy against dihedral angle, and again you will have a staggered and an eclipsed, a staggered, eclipsed, and so on. However, the difference in energy here in this case would be equivalent to 14 kilojoules, 14 kilojoules per mole. So all the top parts represent the eclipsed, and then the bottom, these bottom parts of the graph represent the staggered, more stable conformer. Okay, now we'll do one more before we end our discussion, that is about butane. Okay, now as the number of carbon atoms increases, then the conformation situation becomes more and more complex. Okay, so we will probably do butane or up to pentane, but after that it becomes more complex, and so try to do examples up to 5 carbon atoms. Okay, I mean conformational analysis up to 5 carbon atoms. Now in case of butane, we have a lowest energy arrangement, and in case of butane it is called as an anti-conformation. That's because this is the first one that is shown here. This is my anti-conformation, where the two methyl groups are as far apart as possible, right? It's about 180 degrees away from each other. And then when you rotate along the C2, C3, so here we are actually looking along the C2, C3 axis and giving a bond rotation along that axis, you can get the eclipsed conformation. Okay? Now in as you rotate the C2, C3, you get an eclipse, but there are where there will be interactions between the CH3 and H, the CH3H. So the difference in energy between the eclipsed and the staggered is different from what we saw between propane and ethane, because now here there are two CH3 hydrogen interactions, so the energy is about 16 kilojoules in this case. But if you do one more rotation, okay, if you go from that eclipse that we saw to a next one, which is a staggered, now this staggered is different from the anti, because here see the CH3s are close to each other, and there is this incurs what is called as a steric strain. Okay? And steric strain is the repulsive interaction that occurs when atoms are forced close to each other than their atomic radii would allow. Okay, so you can see that they are getting close to each other. So it's a staggered conformer, but it is not as good as the anti-staggered conformer, where the two CH3 groups were as far apart as possible, right? So this involves a little bit of energy. It's about 3.8 kilojoules. Now we take that and do another 60-degree rotation, and you get another eclipse, which is again different from the earlier eclipse conformer that we saw. Why? Because now you have two CH3 groups that are close to each other. Therefore, the interaction, the torsional strain will be much more, and the total strain that is involved with this eclipse conformer is about 19 kilojoules. Okay, so you can see that when you do the different rotations of butane, it goes from a see that's the lowest energy, then it goes to an eclipse, which is about 16 kilojoules, then it comes down to the next staggered one, but this is not as stable as my first anti-staggered conformer. Why? Because the CH3 groups are right next to each other, whereas in anti the CH3 groups were completely away from each other, right? So this interaction will result in a little bit of energy, that's about 3.8 kilojoules. You take the stagger and do another 60-degree rotation, you go to the eclipse. Now this is my highest energy conformer because here the two CH3 groups are pretty close to each other. You do another 60-degree rotation, you get a staggered, but again where the CH3 groups are right next to each other. So these staggered conformers where the CH3 groups are next to each other, they are what are called as the gauge conformer. And then we have the again the eclipsed, and then we come back to the anti-conformer. So I would like to draw this out one more time and show it to you how it is drawn for practice. Okay, so here is my butane 1, 2, 3, and 4, right? And if you label them as C1, C2, so let's label this as C1, C2, C3, and C4. And if you are looking through this, okay, here is where the C2, C3 bond axis is. Okay, we are keeping our eye here and looking through this. So these are my two carbon atoms that I am focusing on and see what is attached to it. So we'll color this as before. My front carbon atom is my green one, okay, and my back carbon atom is my pink one. Now, what are the groups that are attached to each one of them? On the pink carbon atom, I have a hydrogen, another hydrogen, and then a CH3 group. See, this is a methyl group, CH3 group. At the back carbon atom, I have a and the same thing, a hydrogen, another hydrogen, and then a. Alright, so let's erase all the select marks. Focus on what we have here. Let me go ahead and redraw this one more time. Okay. 1, 2, 4. Keep the green for my front. So I'll also color this CH3. So this is my front carbon atom. Then I have this back one. 1 methyl, the 2 hydrogen atoms. Okay. Alright, so keeping my green as the front, that will be my solid circle. The hydrogen atoms are drawn. Then the other group is a CH3. The back carbon atom is a empty circle. At the edge, we put the hydrogens. So you can start with any structure. Okay, it doesn't matter. So this, the way I drew, it looks like I have a gauge structure to begin with. Right? I have a gauge structure. Because see, when the CH3 groups are close to each other, and this interaction is what is giving me that 3.8 kilojoules per mole of energy. Okay, so it's a stagger, but it has a name to it. We call it as a gauge conformer. Now you take this and do a 60-degree rotation clockwise. Okay, so that means we are moving this way. What do I get? An eclipse. Again, as I said before, I'd like to keep the one of the carbon atoms intact. So I'm going to keep my front carbon atom intact and just rotate the back one. Okay, so when I rotate the back like a wheel, see this hydrogen goes behind the CH3 now. Oh, sorry, that's a CH3. This one should be a CH3. Okay. So this pink hydrogen now goes behind the CH3. This pink CH3 now goes behind this hydrogen, and this pink hydrogen goes behind the green hydrogen. Okay, so this is my eclipsed conformer. Here the total number of energy that is, or the amount of energy that is involved is between every CH3 hydrogen interaction, it's about 6 kilojoules. This is another 6, and this is 4. Okay, so 2 hydrogens interacting torsional strain is 4. A hydrogen and a methyl interacting is always 6, and a hydrogen and another methyl is 6 again. So how much total we have? 12 plus 4, 16. So this eclipse conformer has 16 kilojoules per mole energy, higher than the staggered conformer. Now you take that and do another 60-degree rotation. What will happen? So we will keep the front carbon atom intact, no change in that, so they remain in the same position, the 2 hydrogen atoms and the methyl group. But now the pink carbon atom, which is behind, we do another 60-degree rotation, right? So that hydrogen moves over here, this CH3 group moves over here, and then this pink hydrogen moves over here. Now this is my more stable conformer. See, the 2 CH3 groups are opposite to each other, so this is what is called as my anti-conformer. Anti-staggered. It's a staggered, but it has got a name to it. Anti, and this is the most stable because the 2 CH3 groups are away from each other. Take that, give another 60-degree rotation, and you keep getting you get the eclipsed conformer. Okay, so have same thing. The front carbon atom intact. We have hydrogen atom CH3, and then the pink one at the back. So now this hydrogen goes behind this, the CH3 goes behind this, and we have the hydrogen coming behind this. Okay, another 60-degree rotation. Now we get the most unstable structure, right? Hydrogen into the methyl, but now see, when I do the 60-degree, this CH3 is going to come over here behind the green CH3. Okay, so the pink CH3 is now coming here, the pink hydrogen here, and the other pink hydrogen here. So this one, if you see, the 2 CH3s are very close to each other, and the interaction between them is about 11 kilojoules. These two are 4. This is another 4, correct? So we have 11 plus 4, 15 plus 4, a total of 19 kilojoules per mole. Okay, so as you see, as the number of carbon atoms increases, the conformation situation just keeps getting complex, more and more complex. So I would suggest that you look into more examples of conformations of different molecules, but maybe keep the carbon atom number to about 5 carbon atoms, and also keep in mind that the total number of the energy cost that these for the interactions of each of these groups. You can use this table to find out estimate the relative energies of different conformers. So again, remember that one particular isomer is more stable than the another. It doesn't mean that the molecule adopts and maintains only the more stable conformer. Okay, so it just means that at room temperature, the rotations around the sigma bonds keep on occurring so rapidly that all the conformers are in equilibrium, but at any given moment, a large number of molecules will be present in the more stable conformer than the other one. Okay. So in the next video, we will practice a few problems on chapter 3, maybe one of the worksheets, and you can see how the problems are solved regarding all these topics.